Welcome to Homework Lib.
This question is a mechanism reaction. Specifically, they give us the mechanism for the decomposition of ozone to O2. It's proposed as a two-step mechanism where ozone first decomposes, likely due to a high energy photon, into O2 and a radical or free oxygen atom. This is fast and reversible. The second process then is the radical oxygen that is very reactive will combine with ozone, producing two oxygen molecules. This is slow, so this would be the rate determining step. The overall process then is going to be the sum of these two reactions, and when we sum these two reactions, you'll notice that oxygen is the intermediate. It was created and then later consumed, and we get two O3s going to three O2s. If the slow step is the rate determining step, then we can write the rate law from the molecularity or the stoichiometry of this slow step. The rate is going to be equal to oxygen raised to the first power, because it has a coefficient of 1, multiplied by the O3 concentration, also raised to the first power, because it has a coefficient of 1. The problem with this rate law is it contains the intermediate. We don't want the intermediate in our rate law. We only want reactants in our rate law, or sometimes products, but definitely not an intermediate. If the first step is fast and reversible, then we can say that the rate in the forward direction, because it's reversible, is equal to the rate in the reverse direction. The rate in the forward direction is going to be equal to some constant multiplied by the concentration of O3, and the rate in the reverse direction is going to be equal to some constant multiplied by the concentration of O2 multiplied by the concentration of just O. Rearrangement of this expression allows us to determine what the concentration of O is as a function of the concentrations of the reactant, O3, and the product, O2. This will then be helpful because we can now take this expression for O2 and plug it into the rate determining step in order to get a better rate law for this mechanism. When we do that, we'll get rate is equal to a ratio of these three K values, which can all be combined into a single K value, which I'll do here in just a second, multiplied by the O3 concentration squared. This O3 and this O3 gives us O3 squared, and then we still have O2 in the denominator. And when we combine all the K's together, then it will look something like this. You may choose to write it this way, or you may choose to put the O2 to the -1 power. So it would be an order of -1. It then wants us to determine whether or not oxygen is the catalyst or the intermediate. We already defined it as the intermediate. The last part of this question asks if instead the reaction occurred as a single step, as shown here, if this were a single step, then would the rate law change? Well, the rate law of the single step, if this were a single step, if the overall reaction were a single step, then we could write the rate law from its molecularity, and it would simply be equal to rate equals K ozone concentration squared. This is definitely different than what we determined down here, because we do not have the O2 in our rate law. So yes, it is different.